Introduction to Randomized Optimization in Machine Learning. Hello, everyone. Welcome to the lecture on Introduction to Randomized Optimization in Machine Learning. We're going to be exploring probabilistic approaches for enhancing machine learning performance. So, introduction, let's go over optimization first. Optimization is a key process in machine learning. It is essential for training models, minimizing error functions, and improving overall performance. Uh, so for this lecture, we're going to focus on randomized optimization, a set of methods that introduce randomness into the search process to find optimal or near optimal solutions. And these methods are particularly useful when dealing with large, complex, or non-convex search spaces. Optimization problems in machine learning. So in machine learning, you get to encounter various types of optimization problems. And these can be broadly classified into continuous optimization, where we seek to find the minimum or maximum of continuous function, and discrete optimization, which involves selecting the best solution from a finite set of possibilities, and combinatorial optimization, where the goal is to find the best combination of elements. Common objective functions include loss functions like mean square error for regression tasks and cross entropy loss for classification tasks, as well as performance metrics such as accuracy, precision, and recall. So here is just a simple example. So if we look at this continuous function, we can see a simple quadratic function with a sinusoidal components. So we can find minimum or maximum of this continuous function. We look at this discrete function, we can see that there is a predefined set of values, and this function selects from a predefined set of values. And combinatorial function, you can see that this function sums the squares of elements in a combination. Traditional optimization methods. So traditional optimization methods like gradient descent and its variants are widely used in machine learning. So gradient descent, what it does is it iteratively moves towards the minimum of a function by following its gradient. And variants include stochastic gradient descent, mini-batch gradient descent, and momentum-based methods. However, these deterministic methods have limitations. The limitation is that they can get stuck in local minima, so require gradient information, and may not perform well with non-differentiable or noisy functions. So we're covering more on traditional optimization method, such as gradient descent, in a different lecture, but just to give you an overview, we have a function to optimize. So this is the function that we aim to optimize. And we have this gradient descent simple implementation that iteratively updates the solution. So we can see that uh, gradient descent has parameter learning rate, iteration, and start point, and it's just gonna keep iterating until uh, it finds the optimal value. Introduction to randomized optimization. So randomized optimization methods, unlike traditional optimization method, introduce probabilistic elements into the optimization process. So unlike um, we said that deterministic method, they follow a set path based on gradients. Randomized methods use randomness to explore the search space. This helps avoid local minima and enables broader exploration. So by incorporating randomness, these methods can find better solutions for complex and challenging optimization problems. And here is just a simple example. And we have random search function, and this has function as a parameter, bounds, and iterations as a parameter. And we can see that we have best solution, we initialize best solution and best value, and we will just iterate based on the iteration parameter provided. Since the iteration parameter is 100, we're gonna run for loop for 100 times, and this candidate, we get any random value from uniform distribution that is within the bounds provided, and then it's going to provide this random candidate value into the function and get candidate value. And only if candidate value is less than best value, we will update best value and best solution as well, and we will return best solution. So we will just do this 100 times and find the best value and solution that is a value within the uniform distribution of bounds. Common randomized optimization techniques. So there are several randomized optimization techniques commonly used in machine learning. Simulated annealing is inspired by the annealing process in metallurgy and uses a temperature parameter to control the probability of accepting worse solutions as it explores the search space. Genetic algorithms, it's inspired by natural selection, use crossover, mutation, and selection to evolve a population of solutions toward better fitness. Last one, particle swarm optimization. Uh, so this one models the behavior of a swarm of particles where each particle adjusts its position based on its own experience and that of its neighbors to find optimal solution. Applications in machine learning. So randomized optimization techniques have various applications in machine learning. They are particularly effective for hyperparameter tuning, efficiently exploring the hyperparameter space to improve model performance. And these methods are also used for feature selection, helping identify the most relevant features for building predictive models. Additionally, randomized algorithms can optimize the weights and architecture of neural networks, enhancing their training process. Advantages and disadvantages. So, randomized optimization approaches offer several strengths. They can handle complex, non-convex, and noisy optimization problem, and their ability to escape local minima allows for broader exploration of the search space. And these methods are versatile and can be applied to a wide range of problems. However, they also have challenges. Randomized approaches can be uh, computationally intensive and sensitive to parameter settings. Moreover, there's no guaranteed convergence to the global optimum. So this can be a limitation in certain scenarios. Example, we're going to look more into this when we are covering each algorithm, but just to give a brief example, say you want to use a general genetic algorithm for hyperparameter tuning. Then the step would involve initialization, where we generate an initial population of solutions, selection, where you choose the best solutions based on fitness, crossover, where we combine pairs of solutions to create offspring, mutation, where we introduce random changes to maintain diversity, and evaluation, where we assess the fitness of the new solutions. So by comparing the performance of the model with and without randomized optimization, we can observe the trade-offs and improvements achieved through this approach. Conclusion. So randomized optimization provides methods that is robust for solving complex optimization problems in machine learning. These methods can complement traditional techniques uh, by offering flexibility and adaptability. So looking ahead, we can see possibility of integrating randomized optimization with deep learning and reinforcement learning. So developing hybrid methods that combines deterministic and randomized approaches. This is it for this lecture. Thank you everyone for listening.